This is a new place, but we are back to doing what we want to do, which is to learn about tropical dynamics and atmospheres and oceans. Okay, so chapter 12 is on arid and desert climate. It's a very, very brief chapter, but there are two key concepts. One is the interactions between the desert and the monsoon. So there is a monsoon desert hypothesis which is very important, and we will look at other heat balance terms over the desert and cute things like a jet that develops because of the way heat balance happens during the day and during the night. What is the definition of a desert region? If you just go by precipitation, it's less than 250 millimeter per year of precipitation. Obviously, the polar regions then become really strong deserts with very little precipitation. But here we will just focus on the subtropical arid and desert climates because we are still doing the tropical dynamics, right? We have casually said all along that the deserts are in the subsiding branch of the Hadley cell, and subsidence comes with clear skies, high pressure, no rain. Makes sense. But it turns out that it's not that simple, especially when you look at the stream function that we looked at in chapter 10.5. This is a seasonal cycle looking at June, July, August, September, October, November, DJF and MAM. JJA is obviously the ITCZs in the northern hemisphere. It's when the rain happens, and you would think if deserts are under the subsiding branch of the Hadley cell, then you would see a strong subsidence over the deserts. But you can see that that subsidence is actually the strongest in December, January, February, and not in the rainy season. Of course, one could argue that zonally averaging over the ascendant regions like the monsoons could lead to a weakening of this subsidence, but we will see that actually we will need additional subsidence, which in fact turns out that can come from the monsoonal heating, which is in the subtropics. So the desert mechanisms are not as simple as just saying Hadley cell subsiding branch causes it. Actually, that also expands to the so-called subtropical highs over the oceans. The strength of the subtropical highs, which are like the ocean's deserts, which is where the Hadley cell subsides over the oceans, also have interactions at the boundaries that are related to heating over lands from the rainy regions like the monsoons. So you can see here the global precipitation bands, of course, during JJA, which we can see much more clearly here with the circulation. We have some moisture supply with the southwesterly winds into the monsoon region, Bay of Bengal, Marine ITCZ, and then you have the other ITCZ moving with the sun. So you can see all the precipitation is way over here, and during DJF it moves way south. Right, so the entire thing is moving back and forth, with the difference being that over the Indian Ocean, as we talked before, and we will see again later on, the ocean is pretty warm. So even during the summer months when the sun is to the north, you still have a marine ITCZ, and the ITCZ kind of splits up, and we had upwelling here, and we have deserts over here. So what are the interactions between these deserts and the monsoon, for example? Is it one-way interaction or two-way interaction, and so on? So all these are interesting features. There are of course deserts elsewhere also in the southern hemisphere, and so on. So we will come back and look at the dynamics of the deserts in the next podcast. Since it's a small chapter, I'm going to keep these also relatively small, and we will mostly focus on the data that's available from the past field experiments, where we can look at the heat balances, and what is unique. We have talked about moist processes in chapter 8 as being so critical for tropical dynamics, and these subtropical deserts obviously are bone dry. So what are the processes of creating vertical motion and heat balance? That is a very interesting study by itself as well. Okay.